The Nernst equation is a fundamental concept in electrochemistry. It helps us calculate the voltage or potential of an electrochemical cell under non-standard conditions. The equation is written as E equals E naught minus RT divided by NF times the natural logarithm of Q. Here's what each term means. E, the actual cell potential. E naught, the standard electrode potential measured under ideal conditions. R, the universal gas constant equal to 8.314 joules per mole per Kelvin. T, the temperature measured in Kelvin. N, the number of electrons transferred in the reaction. F, Faraday's constant, approximately 96,485 coulombs per mole. Q, the reaction quotient, which represents the ratio of products to reactants. Now let's look at the two important equations derived from the Nernst equation, the oxidation and reduction half reactions. For the reduction half reaction, E reduction equals E naught plus 0.0591 divided by N times the logarithm of the concentration of Mn plus ions. For the oxidation half reaction, E oxidation equals E naught minus 0.0591 divided by N times the logarithm of the concentration of Mn plus ions. Both equations show how the concentration of ions influences the electrode potential. This plays a crucial role in electrochemical reactions, batteries, and corrosion processes. Now that we understand oxidation and reduction, let's explore three important applications of the Nernst equation: redox reactions, acid-base titrations, determination of solubility of sparingly soluble salts. Let's begin with redox reactions. In redox reactions, the Nernst equation helps determine the potential of a redox system. For example, in the reaction where potassium permanganate oxidizes ferrous ions into ferric ions in the presence of acid, the equation is E equals E naught plus, open parenthesis, R times T divided by N times F, close parenthesis, times the natural logarithm of the concentration of iron 3 plus, divided by the concentration of iron 2 plus. Here, the electrode potential depends on the concentration of iron 3 plus and iron 2 plus ions. To minimize fluctuations, the titration is carried out in the presence of an excess of acid. Now let's explore how the Nernst equation applies to acid-base titration. In an acid-base titration, the potential of an electrode depends on the concentration of hydrogen ions in the solution. For example, when hydrochloric acid, or HCl, is titrated against sodium hydroxide, or NaOH, a hydrogen electrode is placed in the HCl solution. It is connected to a reference electrode, such as a calomel electrode, to form a galvanic cell. The cell potential is given by the equation E equals E of the calomel electrode minus E of the hydrogen electrode, or E equals 0.2422 minus 0.0591 times the logarithm of hydrogen ion concentration. Rewriting it in terms of pH, the equation becomes E equals 0.2422 plus 0.0591 times pH. As sodium hydroxide is added to the acidic solution, hydroxide ions react with hydrogen ions, reducing their concentration. As a result, the pH increases, which in turn affects the electrode potential. Initially, the change in the electromotive force, or EMF, is slow, but as the equivalence point is approached, it rises sharply. After the endpoint, the pH increases gradually again. By measuring the EMF after each addition of alkali and plotting it against the volume of alkali added, the endpoint of the titration can be determined accurately. Now let's explore how the Nernst equation helps determine the solubility and solubility product of sparingly soluble salts. The solubility product, or KSP, of a salt like silver chloride, or AgCl, can be calculated by measuring the electromotive force, or EMF, of a suitable concentration cell composed of the salt under investigation. For example, to determine the solubility of silver chloride, the following electrochemical cell is constructed. Silver solid in contact with silver chloride solid in the presence of 0.01 molar potassium chloride is connected to another silver electrode, which is immersed in a silver nitrate solution of known concentration, also 0.01 molar. These two solutions are connected through a salt bridge. A small amount of silver chloride dissolves, providing silver ions in solution. The cell operates as a concentration cell, where one silver electrode is in contact with a solution of known silver ion concentration, while the other electrode is in contact with a much lower silver ion concentration due to the limited solubility of silver chloride. The EMF of this concentration cell is given by the equation E equals 0.059, 1 times the logarithm of 0.01 divided by C. Here, C represents the concentration of silver ions provided by the dissolution of silver chloride in the potassium chloride solution. By measuring the EMF of the cell, the value of C can be determined. If potassium chloride is assumed to be completely ionized, then the chloride ion concentration is taken as 0.01 molar. The solubility product, KSP, of silver chloride is then calculated using the equation. KSP equals the concentration of silver ions times the concentration of chloride ions, which is equal to C multiplied by 0.01. This experiment helps in understanding how the solubility of a salt can be determined using electrochemical methods.